Hi everyone. Today we'll be solving trapping rainwater problem. The problem statement is we are given a list of integers and we have to visualize them as bars and we have to see how many cubes of water we can trap between these bars and return that as an answer. So there are multiple ways to solve this problem. So there is a brute force approach that goes one bar at a time, and there is also another brute force approach that goes one level at a time. And there is like let me show you all the approaches here, right? So there is this brute force approach is order of n square that solves the problem one bar at a time, whereas this horizontal layer scan solves it one level at a time. These two are not optimal solutions. We have the most optimal solution, which is two-pointer, but that is something that we won't see in this solution. We will look at the monotonic stack, which we'll visualize this solution mainly because monotonic stack is an important algorithm that you have to have in your toolbox to solve other hard problems, right? So that is what we'll be like looking at and visualizing. Now, before we go into the actual algorithm, we will understand what a monotonically decreasing stack is. Right? A monotonically decreasing stack typically looks like this. This is actually the input array, but if we go one element at a time, and if we add it to a monotonic stack, what we will do is what we'll do is like all the bars will get pushed. Here's the stack, right? So it's a separate data structure and we push all the bars. Whereas if we have another example where it is the bars are increasing, what happens is the bar gets added as the top in the monotonic stack, but as soon as a higher element comes, that top gets popped out and then the new element gets added. Right? Ignore these labels for now. We'll come to it later. But this is for us to understand how a monotonically decreasing stack works, right? So if the top of the monotonic stack bar is going to be is going to be larger than the new candidate, then we add it. Let's say we add another bar here, right? So let me add like another bar. Okay. Now what happens here is still this bar, or let me increase the bar here. Okay. Now what happens here is we keep adding these bars to the stack till we reach this point. Once a much taller bar comes in, what happens is all these bars gets deleted and this becomes the first element in the stack. And the next candidate is smaller than this, so this also gets added in the fresh iteration of the stack. Let's go with this example and see how this works, right? So till this point, all the elements are added, but once we have something that is larger, all of the elements gets popped out, right? And what we have here in the stack is just this one element. Now we meet a smaller guy, so that gets added. Let's say, if there is something that is larger, then this stack gets eliminated. So this is how a monotonic stack works. Okay, now before we step into this algorithm, we will understand a basic use case, right? So we have a three-bar chart. Now the bar on the right, we call it the right wall. The bar on the left, we'll just call it left or top of the stack, right? And this we will call it as a basin, right? So if the heights of the left and right bars are changing, what happens to the water level here, right? So whichever is the smaller bar of of these two sides, that is how much water it can trap. So this is a base use case for us to build on top of. Okay, now let's understand the algorithm for this base use case And after that, we'll go for a slightly more complex use case and see how that goes. Okay. So this is the full solution. I'm going to turn off the solution and go step by step, right? So what we do is iterate over the list from left to right and see what can be added to the monotonic stack. Keep pushing and popping them. So that is how the solution is going to iterate over. So the very first bar, the stack is empty. So what we have as a stack is a monotonically decreasing stack. Since it's empty, we just add it. Now we go to the next bar. So the next bar is smaller. It is decreasing. So we add it. Okay. So now we go to the next bar and we find that this bar is taller than the top of the stack. So what we are iterating over are all right wall candidates. So once we come to a situation like this, where the candidate, the element that we are iterating over, is larger than the top of the stack, what we do is we pop the top of the stack and make it a basin. Okay, so now this is a basin. And then whatever is remaining in the stack, we make it the left wall. Now we do our calculations to see how much water this particular basin width can hold. And then, yeah, that's the solution. This is the solution for the base case. Now let's look at something slightly more complex. Now let's look at the example that we've actually seen in the problem, right? So this is the example, and this is how the solution will look like. So remember we saw that, we will need 3 bars for us to meaningfully have some water trapped, the right wall, the left wall, and the basin. And that is what we will be like looking at as we iterate over our bars, right? So we start from left to right, and we start with an empty monotonic stack. So each time we iterate over a new bar, we keep that as our right wall candidate, and we see that if it can be added to the stack. So the stack is empty, so we add 0 here, and then we move to the next one. Now we have the bar that is our right wall candidate that is larger than the top of the stack. If this element is larger than the top of the stack, what do? We pop the stack, the top of the stack, and make that the candidate for the basin. And then we look at whether we can have a left wall. The left wall is supposed to be whatever is remaining as top of the stack. Now the stack is empty, so we can't form the trinity of left, basin, and right. So we do not put any water here, and we move to add this element as the only element in the stack. Now we keep going, we find a smaller element, which means it is allowed to be appended to the monotonically decreasing stack. We add it, and then we move, and we find a right wall candidate that is larger, and the top of the stack is smaller. What do? We can't add a larger element to the stack. So we pop the top and make that a candidate for the basin. Now we have something left in the stack still, which means that will be the candidate for the left wall. Now we have a perfect trinity. What do? Of the left wall and the right wall, we look at what is the smaller height. This is the smaller height, and this is what we'll have to delta with the basin. So this, the height of this is 0 and the height of this is 1. So we'll be filling 1 water cube here. Now there is also a width calculation that we'll have to do, but we'll come to that later. Here we'll just know that the width is 1, so we fill water here. Okay. Now what do? We pop the older elements in the stack and then make this the only element in the stack. Okay. Now we are having a decreasing sequence, so we add all of these to the stack. All these 3 elements are added to the stack until we reach a bar that is larger than the top of the stack. So We pop the top of the stack, this is popped, and this is what is remaining in the stack. We have a perfect trinity. So what do we do? We look at whatever is the minimum between the left and the right. Here both are the same, so it doesn't matter. Now we look at the delta between the basin and the wall. It is 1. So we put 1 water cube here. Now, uh, we will go to the next element, and the next element is going to be uh, the same as this. So we just add it here, the same as the top of the stack. Since it is not higher, we just add it. We go to the next element. Now this is a larger element, which means we have to pop the base, right? So we pop the top of the stack, and whatever is the top of the remaining stack acts as the left wall. Here we have an interesting use case, right? So we look at the right wall and the left wall and see which is the minimum here. Here, this is the minimum. Now, the basin and the left wall does not have a delta. They are basically the same height, which means we do not add a water cube here in this iteration. Okay, so we can see the calculations here. We'll come to it when we look at the code in detail, but basically we don't add any water here. That is the gist of it. So now we go to the next right wall candidate, which is larger, right? uh, so let me go to let me actually put this guy into the stack, then we'll be able to go. Yeah. Uh, Sorry, we didn't put this. This is more of a right wall candidate. We haven't placed it in the stack yet. So we popped the previous element, which was previously the left wall. Now it's a basin, and then what is remaining in the top of the stack is the left wall. Now, if we compare the left wall and the right wall, we see that the left wall is smaller, but it is at least taller than the basin, which means we can add water cubes. But do we add water cube to just this basin, or do we do a sweep of all three here? What we'll do is we'll do a sweep of all three here and add 3 water cubes here. Now, how do we do that? Let's go into that calculation, right? So now in the stack, what we actually store is the index of the particular bar. So the right and left index -1 will give us the width. Here is the left and here is the right. If we do a difference here, we will get the width as 3. Now we calculate the bounded height. What do we mean by the bounded height? So the we take the minimum of the left and the right. Here it is 3 and 2, and the minimum here is 2. And we subtract the height of the basin or the bottom here. So the bounded height will be 2 minus this 1, which will be 1. And now we have the width and the bounded height. We multiply them. So this will be 3 multiplied by 1. So the answer would be 3. And that is what we will add to the total water. Hope this is clear. So now what do we do? We will make this as the only element because all the elements to the left are lower in the stack. So we make this the only element, and then we keep going. Here we will here it is in a decreasing sequence, so we just keep adding it to the stack, and once we find a larger element, we pop the top of the stack, and then we have a perfect trinity. We put a water cube here. And we are pretty much done with the program. What is remaining? The remaining iteration is just a chore. So we just keep going, adding to the stack. Now we have the stack, but we are already at the end of the iteration. So we have all our water cubes calculated, and we return that, right? Now that we have seen our visualization, the code here will be easy to follow. First, we initialize a stack, and then we have water that will calculate the total water that we need to return. So as we iterate over the list, we are considering all of those iterations as a right wall candidate. Now, if the stack is there, and if the right is going to be higher than whatever is the top of the stack, then we enter into popping it and doing some calculations. Otherwise, we just simply append to the stack, right? So let's go into this calculation. What do? We pop the stack, and then we make that as the basin, the bottom, right? And then if there is nothing left in the stack, if there is no left wall for us to form the left wall, right wall basin combination, then we just break, we don't do anything. If there is a left wall, then we do our calculation, right? We want to first calculate the width, for example, in this use case, right? So when we are reaching this use case, we need to calculate the width of tree. That's going to be right minus left minus 1, right? So and then we are going to calculate the bounded height. For example, when we are in this area, we should not be having the bounded height as 2 here, because this is a block that we already solved. We only want to solve this particular height, right? So the bounded height has to be calculated to 1. How do we do that? We take the minimum between right and left and then subtract the height of the basin itself, and that will give us the bounded height. And then we multiply the width. Here the width is 3 and the height is 1. So we'll be adding these 3 water cubes in this particular use case that we are talking about, right? So, and then we, irrespective of what happens, we append the right candidate, and then we keep moving. Hope the solution helps. See you in the next video. Thank you.